Welcome to clickmyproject.com. Our product title is Glitch Energy Reduction and SFDR Enhancement Techniques for Low Power Binary Weighted Current Steering DAC. Next we see about abstract of our product. VLSI technology is to optimize any type of digital architecture because this type of optimization process is mainly used to enhance the various applications. The main objective is reduce the glitch energy. Glitch energy is optimized by using of dynamic capacitance compensation. The SFDR is improves at high signal frequencies by using of binary weighted current steering digital to analog converter. SFDR is nothing but spurious free dynamic range. To minimize the clock period by using retiming latches technique, thus provide increased speed, linearity and power. To reduce the integrity linearity error and differential linearity error, this project involves a glitch reduction approach by dynamic capacitance compensation of binary weighted current switches in a current steering digital to analog converter. The fundamental circuit of most D by A converter involves a voltage or current reference, a resistive ladder network that derives weight currents or voltages, usually as discrete fractions of the reference, and a set of switches operated by the digital input that determines which current or voltage will be summed to constitute the output. The output of the D by A converter is proportional to the product of the digital input value and the reference. This design is carried out by CMOS technology in Tanner EDA tool. Next we see about flow diagram of our product. In this product we using current steering digital to analog converters that performs an important role in communication and video systems. Current steering digital to analog converters have the advantages of speed, linearity and power efficiency. There are three different architectures to implement the switched current source: array, binary and unary segmented, and that account for power consumption, chip size and circuit complexity. The binary weighted architecture is still a good candidate for medium to high resolution and also sampling rate. It achieves both static and dynamic specifications at low cost. The design approach proposed to apply the LSP part for segmented digital to analog converter. In this flow diagram consists initially the digital signal is fed into the input buffer. The digital signal is a 16-bit data and the data is fed into the input buffer. Buffer is nothing but is an amplifier that provides an interface between mismatched circuit elements. It is a unity gain amplifier packaged in an integrated circuit. Its function is to provide sufficient drive capability to pass signals or data bits along to a succeeding stage. The voltage buffers increase available current for low impedance inputs while retaining the voltage level. The current buffers to just the opposite, keeping the current the same while driving high impedance inputs of higher voltage levels. Next one, the output of the buffer is fed into the flip-flop. Flip-flop is nothing but is important for the clocked flip-flops as it ensures that input S and R never equal to 1 at the same time. The T-type flip-flop are constructed for a gated SR flip-flop with an inverter that ordered between the S and R inputs to allow for a single D input data. Then the single data input labeled D is used in place of the Z signal. Thus this single input is called data input. If this data input is held high, the flip-flop would be set. and when it is low the flip-flop would change and becomes it reset. Next one, the dynamic capacitance compensation. The output of the flip-flop is fed into the dynamic capacitance compensation. This block is used to compensate the output glitches from the flip-flops. And next one, this compensation is fed into the binary weighted current switches digital to analog converter and with retiming latches. Using of binary weighted current steering, the digital to analog conversion is converted in high efficiently. And finally, the output analog signal is fed in the output side through a RC network. The RC network is a filtering components that filtered the unwanted noises and signals in the output signal. Next, we see about running process of our product. In our product is done in CMOS technology using of Tanner EDA tool. This is the Tanner EDA tool, especially a edit spice simulation tool. First open the file and select the new and new design. Now the window is open. Then we select the specify cells. For example, cell 0, cell 1. First create a one cell. That cell is cell 0. In cell 0, in our product, that design the with compensation of 2-bit digital to analog conversion. This is the circuit design of digital to analog conversion for 2-bit data, and this is the circuit design for 2-bit data but without compensation. That means there are no capacitor compensation are connected in the dynamic range. And next one, our product main design is here. Totally 16-bit data is given into the input buffer. That input buffer is buffering the digital signal into the D flip-flop. In the D flip-flop, given clock signal, that output will be displayed depend on the clock signals. And after that, the D flip-flop output is fed into the PWCS. That means binary weighted current switches current steering digital to analog converter block. And after that, BWCS DAC is converting digital to analog. After that, analog signal is compensated using of dynamic compensation. After, the output will be displayed in this specific window. Then simulate the corresponding window. The output will be displayed. First one, this is the corresponding output of our product. This is the voltage. This is the analog signal. This is the input signal for our product. The input signal is here, digital signals. So 0 1 0 1 is changes, and the output is the analog signal. So this varies 0 to 600 and next down to 0. So this is an analog signal. So this is our corresponding output. And the next one, the output time delay is shown in here. This is the time delay for our product. This power time delay is generated in the specify window of DSpice, and also using of this DSpice, the power will be calculated. For example, you open cell 7, selected DSpice files will be open, then simulate the corresponding window, the output power will be generated. Here the power value is given, so then run the simulation. The output power window will be open in the corresponding output display window. This takes some several seconds. The time is a time delay seconds. The corresponding power output will be shown. This is a voltage, input voltage, and this is the power of our product. The overall glitches will be reduced in the output waveform voltage, and also it improve the conversion rate, and time is reduced, overall area is reduced. So using of binary weighted current steering digital to analog conversion having lot of advantages over the conventional digital to analog conversion.